Every time you open a website, your browser has to answer one question. Can I really trust who I'm talking to? Without a strong answer, the internet would be chaos. Anyone could pretend to be anyone, and you'd have no way to spot an imposter. Public key infrastructure is the identity system that brings order to that chaos. It gives every trusted website and service a cryptographic ID card, a certificate and key pair issued by a recognized authority. TLS then uses those keys to deliver what we rely on every day: confidentiality so others can't read your traffic, integrity so it can't be silently changed, and authenticity so you know who's at the other end. In this module, we'll unpack how that trust is created and maintained during HTTPS connections, and why the details of the TLS handshake, mutual TLS, and mechanisms like certificate pinning are so critical to a secure internet. When you see HTTPS in the browser, what's really happening is TLS giving you 3 guarantees, all built on top of PKI. First, confidentiality. The actual data is protected using fast symmetric encryption. So even if someone captures the traffic, they can't read it. Second, integrity. Hashing and message authentication codes make sure the data isn't modified in transit. If a single bit changes, the tampering is detectable. Third, authentication. Here's where PKI comes in directly. Asymmetric cryptography and certificates let your browser verify that the public key it's talking to really belongs to the domain you requested. PKI is the foundation that maps domain names to trusted public keys. Without that mapping, you could still encrypt, but you wouldn't know who you were encrypting to. Before any real data is sent over a secure connection, the two parties have to complete a kind of cryptographic handshake. They begin by negotiating the rules of the conversation. The client and server agree on the protocol version and which cipher suites they both support. This is like agreeing on a common language and set of tools, so everything that follows is compatible and secure. Next, the server has to prove who it is. It sends its certificate chain, which the client validates against trusted certificate authorities. If that chain checks out, the client can be confident it's talking to the legitimate server, not an imposter in the middle. Only after identity is established do they generate shared keys. Using algorithms like Diffie, Hellman, or elliptic curve Diffie, Hellman, they derive fresh shared secrets that never travel directly over the network. Those keys will then protect all application data that flows afterwards. Let's look more closely at that fast trust decision. When your browser connects to a secure website, first, the client proposes how to talk securely, which TLS version, which cipher suites, and which server name it wants. The server answers with its choices, and some fresh random data. The crucial step is what happens next. The server sends its certificate chain, and proves it actually holds the private key corresponding to that certificate. Your device walks that chain up to a trusted root CA and checks. Is the name right? We the highlight image. Has it been revoked? And does the signature verify? That's the PKI moment of truth. Once those checks pass, both sides finish the handshake with an integrity check over everything they just agreed on. From that point, application data is encrypted and authenticated. PKI isn't an add-on around TLS. It's embedded in the handshake, as the decision point where some server on the internet becomes a server I can cryptographically trust. Under the hood, your browser answers that "Can I trust you?" question by walking a certificate chain. At the bottom is the server's certificate. Above that, one or more intermediate CAs. At the very top, a root CA that already lives in your device's trusted store. The browser checks several things along this chain. Is each certificate still within its validity period? Has any certificate been revoked, for example via OCSP? Does each certificate's digital signature verify correctly using the public key of the one above it? And finally, does the server certificate's hostname actually match the URL you typed? Only if all those checks pass and the chain anchors to a trusted root is the identity accepted. If any step fails, the trust decision is simple. The connection is rejected. Once the client and server have authenticated the server's identity, they still need fresh keys to actually protect the traffic. That's where key agreement and key derivation come in. Both sides generate their own ephemeral key shares and exchange them. Using Diffie, Hellman math, each side combines its own share with the other party's share, and independently computes the same shared secret. That shared secret is never sent over the network. We don't use that raw secret directly. Instead, it goes into a key derivation function, which stretches and mixes it into several different keys. One for finishing the handshake, one for encrypting application data, and initialization vectors or nonces as needed. Because these key shares are ephemeral and thrown away after use, we get forward secrecy. Even if an attacker later steals a long-term private key from the server, they still can't go back and decrypt old recorded sessions, because each session used unique, short-lived keys, derived from that one-time shared secret. After the TLS handshake completes, the connection moves into what we call the secure state. At this point, both sides have agreed on which algorithms to use, verified identity using certificates, and derived shared session keys. The final handshake messages are integrity protected, so if an attacker tampers with anything, the connection is aborted, instead of silently accepting bad parameters. From then on, all application data, for example an HTTP request like get/account, is wrapped in encryption and integrity checks using those session keys. To anyone on the network, the traffic now looks like unreadable ciphertext. This separation is important. The handshake is about setting up trust and keys. The secure state is about efficiently protecting every byte that follows. PKI underpins the trust part, and symmetric cryptography takes over to keep the ongoing communication fast and confidential. So far, we've focused on the server proving its identity. With standard TLS, only the server presents a certificate. The client verifies it, the connection is encrypted, but the client itself is still effectively anonymous. That's fine for public websites, but it's too weak for zero trust. Mutual TLS takes this a step further. Here, both sides present certificates, and both sides validate each other. The client proves, "I am this specific service or device," and the server proves its identity back. PKI is what makes this possible. Each certificate chains up to a trusted CA. So you're not just trusting a password or a token, you're trusting a strong cryptographic identity. This model is powerful for machine-to-machine traffic, B2B APIs between companies, service meshes inside Kubernetes, and internal microservices that should never trust the network by default. In all of these, mTLS turns every connection into an authenticated, encrypted tunnel, where identity is verified at both ends, every time. In a normal TLS handshake, the server's identity is proven, but the browser or client stays essentially anonymous. With mutual TLS or mTLS, that changes. After the server presents its certificate, it actively asks the client for one. The client sends its own certificate chain, just like a server would, and then performs a critical step. It proves it actually holds the private key for that certificate. That proof is done by signing handshake data with the client's private key. The server verifies that signature using the client's public key from the certificate. If the check passes, the server knows two things. This certificate is trusted by a known CA, and this specific client controls the corresponding private key. The result is strong cryptographic client authentication, built directly into the TLS handshake without passwords, cookies, or API keys. This is why mTLS is so valuable in zero-trust networks and service-to-service communication. Mutual TLS gives you very strong zero-trust security, but it is not free. Every client and every service needs its own certificate, and those certificates must be issued, renewed, and revoked reliably. Doing that by hand does not scale beyond a handful of systems. In real environments, you need an automated certificate manager to handle issuance and rotation. You also have to define trust boundaries carefully. Each server must know exactly which certificate authorities it will trust for client identities. Otherwise, you either break connectivity or accidentally trust the wrong clients. When something fails, troubleshooting is rarely about TLS itself. It is usually a misconfigured trust store, an incorrect SAN, or an expired or wrong certificate. That's why for mTLS, automation is not a nice-to-have. It is mandatory if you want strong security without drowning in operational overhead. Certificate pinning adds an extra layer of trust on top of normal TLS validation. In a standard connection, your browser or app trusts any certificate that chains up to a trusted CA. That usually works, but it leaves a gap. If a CA is compromised or a certificate is misissued for your domain, an attacker can still present a valid certificate and perform a man-in-the-middle attack. With pinning, the client says, I won't just trust any valid certificate. I expect this specific key or fingerprint. The app stores that expected key in advance. When it connects, it compares the server's certificate fingerprint to the pinned value. If they match, the connection continues. If they don't, the connection is blocked, even if the certificate would normally be accepted by the CA system. So pinning deliberately ignores generic CA trust and replaces it with a much narrower, application-defined trust anchor. Done well, it sharply reduces the impact of rogue CAs, misissuance, and certain interception devices. But it also means you must manage certificate and key changes very carefully, or you can break your own clients. When you implement certificate pinning, you're really making a choice about how tightly you bind your client to one specific identity. Pinning to the exact leaf certificate is the most fragile option. Every time that certificate is reissued or renewed, your clients must be updated too. That can work for tightly controlled environments, but it creates a big operational burden and a real risk of accidental outages. Pinning to the server's public key is usually a better balance. You can renew or change the certificate, as long as you keep the same key pair, so you get continuity of trust without redeploying every client. The broadest approach is to pin to an intermediate CA. Here you're saying, I trust anything this issuer signs. That is far more resilient to routine certificate changes. But if that intermediate is ever compromised, your blast radius is larger. In practice, these pinning decisions show up in hard-coded pins in mobile apps, in SDKs used by many services, and in reverse proxies that front your APIs. For each of those, you should consciously trade off brittleness versus flexibility, and choose the narrowest pin that you can realistically operate over the lifetime of the system. Certificate pinning is powerful, but it comes with real operational risk. When you pin, your app is essentially saying, I will only trust this exact key or certificate. That's great against man-in-the-middle attacks. But it also means any change on the server side can instantly break every client. Think about normal key rotation, or a move to a new CA. If the server updates its certificate, but users still have the old PIN embedded in their app, all connections start failing. There's no graceful degradation. It's a hard error. To manage this safely, teams need tight coordination between app releases and certificate changes. You usually include backup pins, so the app already trusts the next key before you rotate. And you need a plan for emergencies. If a key is compromised and you have to revoke it quickly, pinned clients may be stuck until users update the app. So pinning should be treated as a high-risk, high-reward control. Use it selectively. Automate rotation as much as possible. And make sure product, security, and ops teams are aligned before you rely on it in production. When you design with PKI, you're really choosing how much trust you need and how much complexity you're willing to live with. Standard TLS is the default for the public web. The server proves its identity with a certificate. The client checks the chain, and you're done. It's relatively simple, scales well, and is usually enough for browser-based applications and external APIs. Mutual TLS goes further. Now both sides present certificates, so the server authenticates the client as well. That fits zero trust thinking. Every service call must be authenticated and authorized. The trade-off is operational overhead. You need certificate enrollment, rotation, and revocation for every client, which makes the most sense in controlled environments like internal microservices or service-to-service APIs. Pinning is the extreme end. You hardcode or tightly bind which certificate or public key is acceptable. This gives very strong, very specific trust and can reduce exposure to rogue CAs or misissued certs. But if you rotate keys or change CAs and forget to update pins, you break your own clients. That's why pinning is typically reserved for very high-value use cases where you can tightly manage updates, such as some mobile or critical financial apps. The key idea is not maximum security at any cost, but balancing trust, complexity, and maintainability, so the design is secure and also operable over time.